Hello everybody, I am Ananthavalli from Education channel. Welcome to this new video from my channel. We are continuing class 11 chemistry, classification and periodicity of property. Periodic properties part 16. In this video, we are going to discuss the relation between trend of periodic properties and chemical reactivity. Watch the video completely so that you get all points clear. And if you think the video is useful, do like the video, share the video with your friends, and also leave your feedbacks as comments in the comment box below. If you have not yet subscribed my channel, do subscribe it now and support me. Thank you very much. Come, let us start the video. We have already discussed the trend of a few fundamental periodic properties like atomic radii and ionic radii, ionization enthalpy and negative electron gain enthalpy, electronegativity, oxidation state, etc. In this video, we are going to discuss how this trend of change in periodic properties affect the chemical reactivity of elements. Let us just recall the trend of a few periodic properties. I have already posted individual videos for these periodic properties. If you have not yet watched that, please visit the playlist given under N card in order to watch them. From the table, you can understand atomic radius is maximum on the left hand side and minimum on the right hand side, whereas ionization enthalpy, negative electron gain enthalpy, and electronegativity are minimum on the left hand side and maximum on the right hand side. In a group, atomic radius is minimum at the top and maximum at the bottom, whereas ionization enthalpy, negative electron gain enthalpy, and electronegativity are maximum at the top and minimum at the bottom. How does the trend of these properties, as is shown here, affect the reactivity of the elements? That is our topic. Let us analyze one by one. Ionization enthalpy is least on the extreme left, that is alkali metals, that is first group elements. So they are highly reactive due to high electropositivity. They give away electrons or donate electrons and get oxidized. They are high reducing agents. So the elements on the left hand side are highly reactive, but they are reducing agents. Electronegativity of the elements on the left hand side is very less, so their electropositivity is high. Electron gain enthalpy is maximum negative at the extreme right of the periodic table, that is 17th group, halogens. For the present, we are ignoring 18th group. They are zero group elements and their reactivity is very less. The halogens are highly reactive due to high electronegativity. They accept electrons and get reduced. They are high oxidizing agents. So elements on the right hand side also are highly reactive, but they are good oxidizing agents. So let us sum up. Elements with low ionization enthalpy and elements with high negative electron gain enthalpy are highly reactive. They are at the two extremes of the periodic table, but their mode of reaction is different. What happens in the middle of the periodic table? In the middle, elements are comparatively less reactive. In the extreme left, elements are more metallic, and on the extreme right, elements are more non-metallic. So we may say metallic property decreases from left to right and non-metallic property increases. Some metals in the middle are metalloids. They show the property of metals as well as non-metals. For example, consider the third period elements. Sodium, magnesium and aluminium are metals. Silicon is a metalloid. Phosphorus, sulfur, chlorine and argon are non-metals. We said that in the middle, elements are comparatively less reactive. You get the D block and F block elements towards the middle. Let us see why it is so. But before that, let us see what happens down the group. Down the group, the metallic property increases and non-metallic property decreases. So on the left hand side, as we go down the group, reactivity of the elements increase. What about the right hand side? On the right hand side, as we go down the group, the reactivity decreases. The most reactive elements are at the top. This is due to the difference in these periodic properties. Okay, let us consider the middle elements. Ionization enthalpy value for D and F block elements is between the values for S block and P block. That is, the values are greater than that for S block but less than that for P block. Their metallic property, electropositive property, oxidizing property are all less than that of S block elements. This is also because the change in the atomic and ionic radii of these elements are less for transition elements, that is D block elements, and still less for F block elements, that is inner transition elements. That means their atomic size and ionic size does not change much. Down the group for representative elements, ionization enthalpy gradually decreases. That is, the ability to donate electron increases. That is, their metallic property increases. Negative electron gain enthalpy regularly decreases. That is, the ability to accept electron becomes less. So, non-metallic property decreases. As metallic properties increase, the reducing property also increases. That is, its ability to function as reducing agents increases. This can also be related to the atomic size, which increases down the group. What about the reactivity of transition elements down the group? Down the group, the trend of ionization enthalpy, negative electron gain enthalpy, metallic nature, non-metallic nature, and reducing character is the reverse of the trend of representative elements. But there are a number of exceptions due to the availability of the d orbitals as well. We are talking about transition elements. For the inner transition elements also, there are, in addition to d orbitals, f orbitals as well. In the coming chapters, you will learn about coordination compounds where the transition elements enter into special types of bonds called coordinate bonds. Due to the availability of extra orbitals, they can accommodate more shared pairs of electrons at the same time maintaining metallic property. For now, it is very difficult to give a comprehensive account of the reactivity or chemical nature of the transition and inner transition elements. Anyway, the variation of their chemical reactivity can be related to the change in atomic and ionic radii, which decreases from group 3 to 6, more or less remains constant from 7 to 10, and from 11 to 12, they have a larger radii. This is with reference to the period. Anyway, down the group, we may generalize that the properties generally increase, though there are exceptions. Remember, when atomic radius increases, metallic property increases. So they will have a tendency to form ionic compounds, but due to availability of additional orbitals, they can also accommodate shared pairs of electrons. That is the peculiarity. So they have special type of reactivity. We know chemical reactivity is associated with electron configuration. When a question is asked about the reactivity of transition or inner transition elements, we have now seen that we cannot generalize the nature or trend of the reactivity. But we can say that as d and f orbitals are available in addition, We can say that maintaining the metallic property, they can also accommodate additional shared pair of electrons, that is covalence. I hope I have made it quite clear. Our topic is relation between periodic properties and chemical reactivity. How is chemical reactivity ascertained or understood? Normally, chemical reactivity is understood by studying its ability to react with halogens or with oxygen. In this video, we will consider the reaction of elements with the oxygen. Alkali metals, which are on the extreme left, react with oxygen to form basic oxides. That is, those oxides dissolve in water to form bases. For example, oxide of sodium, sodium oxide, dissolve in water to produce sodium hydroxide, which is a base. Elements in the middle of the periodic table form either amphoteric oxides or neutral oxides. Amphoteric oxides are those which, when dissolved in water, can act as acids with bases and act as bases with acids. Neutral oxides are those which form neither acids nor bases. Aluminium trioxide forms aluminium hydroxide, which is amphoteric in nature. Elements on the extreme right form oxides which dissolve in water to form acids, so they are acidic oxides. Example, oxides of halogen. So across the period, that is from left to right, there is a changeover from strongly basic to strongly acidic. Let us see the examples. Sodium oxide forms strong base, so it is strongly basic. Magnesium oxide is weakly basic. Aluminium trioxide is an amphoteric oxide. Silicon dioxide is weakly acidic. Phosphorus pentoxide is acidic. Sulfur trioxide is strongly acidic. Oxide of chlorine is very strongly acidic. We have considered the representative elements belonging to the third period. First group elements form strongly basic oxides. 17th group form strongly acidic oxides. In the middle, the 13th group elements form amphoteric oxides. Second group elements form weakly basic oxides. 14th, 15th and 16th group elements form weakly acidic, acidic and strongly acidic oxides respectively. I hope this example has helped you understand the gradation in the chemical reactivity of these elements as we move from left to right. If the video was useful, do like the video, share the video with your friends and also leave your feedbacks as comments in the comment box below. If you have not yet subscribed my channel, do subscribe it now and support me. Press the bell button and all button for notification of more videos like this. Thank you very much. We will meet in the next video with another important topic like this. Till then, bye. Take care.